Okay, this is about electric current. Remember, I told you that there are two different types of current. You can have current, electricity, and static electricity. I actually started with static electricity. And we said that static electricity involves charges that are transferred and they stay where they are transferred to. For instance, by rubbing, electrons can be transferred from a pen to your hair or from the hair to your pen and they stay. That's for static electricity. If they can stay charged, static electricity. And the only way you can keep them charged that way, staying charged, is with an insulator. Because with a conductor, the electrons will leak away, as it were. They will have to find a pathway to flow out. So once those electrons are transferred, they should stay at the point they are transferred to and keep that object charged. Because if they find a pathway to flow out, the object becomes discharged. So insulators are good for keeping static electricity. Because static electricity involves charges that are transferred and they stay where they are transferred, keeping that object charged. But when you talk about current electricity, we are now talking about flowing charges. Flowing charges. So the charges have to flow. They actually flow in a loop, in a cycle, flowing charges. So what kind of material can we use for for current electricity? Conductors, or copper, for instance. Conductors that can allow those charges to actually flow. Metals and graphite. You know, graphite is the only non-metal that conducts electricity because of the arrangement of the valence, the free electrons in between layers. All right. Okay, so that's about current electricity. Just a moment. So, in discussing current electricity, we need to look at some of the terminologies. Current, for instance. Current is the rate of flow of charge. So when we say rate, what comes to your mind? When we say rate, what comes to your mind? Exactly, you are talking about the quantity measured with respect to time. So, rate of flow of charge. If charge is Q and current is the rate of flow of charge, it means that current will be charge that passes through with respect to time. The charge that passes through with respect to time. So, current is the charge that passes through with respect to time. By the way, current is represented by the symbol I. So current is the rate of flow of charge, which of course will be Q over T, the charge that passes through with respect to time. Anytime you talk about rate, you are talking about something with respect to time. So current is the rate of flow of charge or quantity of charge over T. The quantity of charge itself is measured in what? Do you remember? We talked about that when we're looking at static electricity. Coulomb, capital letter C. Quantity of charge measured in coulomb. So if I is Q over T, that means Q is IT, isn't it? Q stands for what? Quantity of charge. I, current. T, time. All of this must be in SI unit. The time must be in seconds. Okay. Now, current is measured in ampere using an instrument we call an ammeter. And an ammeter is connected in series. We'll talk about all that when we get to circuit connections. So that's for current. I said current is measured in ampere or amperes or amps, if you like. Using an ammeter as the instrument which is connected in series. We look at all that. That's for current. And of course, just for simplicity of expression, current is presented with a letter I, capital letter I. Then voltage, I will define voltage now and then I will still define it in a broader way. You can think of voltage as the ability of the power source to push out charge. Just an illustration. In fact, voltage can be seen as the amount of push given to the charge. The charge could be given a very large push. So we talk about high voltage, or a little push, low voltage. Think of it as the amount of push. The voltage itself is actually a technical name for potential difference or the electromotive force. It's the technical name we use for potential difference or the electromotive force. I will define all of this one after the other later when we meet those definitions properly. All right. So this is what I mean by potential difference. I can use this illustration to describe what potential difference is. Are you ready for that? Yes. Think of this as you have a pipe. This is a pipe, an open pipe at both ends A and B, with water inside this pipe, lying horizontally. I'm going to represent the water inside the pipe with dotted lines like this. You know, if you have water inside this pipe and the pipe is lying horizontally, even though we have water inside the pipe, but because the pipe is lying horizontally, what I mean by lying horizontally is the same distance from the ground, like from here to here, and from here to here is the same distance. Assuming this is 5 meters, this is also 5 meters. Same distance. A is the same height from the ground. B is also the same height from the ground, isn't it? Yeah. So the pipe is lying horizontally. Yes, it's lying horizontally. And there's water in it. This water in it can stay still, not flowing, because it's lying horizontally. I can make the water flow. Can I ask you, how can you make this water flow? Maybe I have to explain properly before you start answering. I can make the water flow by tilting it. Tilting this pipe now. If I tilt this pipe such that this side now is maybe at a distance of 2 meters from the ground, while the other side is at a distance of, let's even say, 7 meters from the ground. So you still have A and B. They are at different heights from the ground. Different. Look at the word I said, difference. Different height from the ground. So the two ends, and A and B, are at different potentials or different heights in this sense. The two ends are now kept at different potentials so the water can flow. When both of them were at the same potential, no difference. This is 5, this is 5. Any difference? In other words, the difference in potential here is 0. So no water can flow. And now that we have made the two ends to be at different potentials, in this case different height, the water can flow. And of course, the water is going to flow from where to where? From a position of the higher potential to a position of the lower potential. Isn't it? So the potential difference, so that you see it now. Look at another case. Before I talk about what I think you need to understand, look at another case like this. This same pipe is now like this, and let's say this horizontal position is such that here is just maybe 0.1 meters from the ground. Okay, let me make it a little bit better so that we see it better. I have this, assuming this is just 1 meter from the ground, and this one is now has changed to 8 meters from the ground. This is 1 meter from the ground. This is the ground level. Can I ask you, compare the rate at which the water will flow in this case? It will be greater, isn't it? Yeah. Because there's a greater difference in height or difference in potential. What is the difference in height in this case? 0, so no water is flowing. What's the difference in potential here? 5. It can flow because there's a difference in potential. What's the difference in height here? 7, more than this one. So I can give it different letters. This one is case 1. Then this is 2, and this is 3. You can see in the third case, there's a higher difference in potential. So the higher the difference in potential, the more forcefully the water flows. That's why I told you that voltage, which is a technical name for potential difference, can be likened to the amount of push given to the current. In this case, the pipe is like a conductor, like a piece of wire. The water in it is the charge, which could be electrons, right? The difference in height is like the potential difference. When the two ends are at the same potential, even though you have water in it, even though you have charges in them, free electrons, nothing flows. Are you listening to me? But once you make one end at a different potential than the other, the already existing free electrons can now flow. You know, it's only water that is free that can flow. That is why any piece of wire, any conductor, if you remember metallic bonds, you did do chemistry, but you know, in metals have free electrons, delocalized electrons. That's why metals are good conductors of electricity and heat. They have free, that's electrons that are already released in between the atoms. Those free electrons are existing between the atoms, just like the water. This is the metal, this pipe is the metal. Those free electrons are this water I represented with red marker. They are all there, but the wire will just stay the way it is if the two ends are at the same potential. Like end A and end B are the same potential. So the potential difference in this case is what? 0. The free electrons will just stay where they are and not flow. But once one end, like end B, is now kept at a higher potential than end A, the free electrons that were already there can now move, flow. How do I make B to have a higher potential than A? Of course, it's not by tilting, because I just use tilting as an illustration. What I can do is connect end B to say the positive side of a battery and connect end A to the negative side of the battery. Let me say you have a battery like this. You have a battery like this. This is the positive side of the battery. This is the negative side of the battery. If you have a piece of wire this way, the two ends, A and B, are the same potential, nothing flows. But once I bring this wire and connect it from here to here, these two ends, A and B, are now at what? Different potentials. The positive side, if it is the higher potential, will cause the free electrons already inside the wire to begin to flow. Actually, it is B. Electrons actually flow from negative to positive. We'll talk about all that anyways later. Electrons flow from what? Negative to positive. In fact, they are repelled, pushed away from the negative terminal, and they run towards the positive terminal. So that's what happens. So the higher the difference in these two terminals, the more forcefully the electrons can move. So the higher the difference, like the higher the potential difference, the more current flows. Higher potential difference, like III, we produce a greater current, moving electrons, compared to II. I said all of that to give you a simple law we use in physics. We call it Ohm's law. You might have heard of that. Current is directly proportional to potential difference. What did I say? Proportional to potential difference. This is it. Ohm's law states that current is directly proportional to the voltage or potential difference. Okay. Obviously, it has to be that way. Because we said that when you have a higher potential difference, like I, the water will flow more forcefully, isn't it? So that means if you have a higher push, which is like a higher voltage, compared to II, where the potential difference is less, the water still flows, but not as forcefully as III, with a higher potential difference. This side is A, this one is 1N. I'm just using it as an illustration. So the higher the potential difference, that's what direct proportionality means now. When something is directly proportional to the other, what does it really mean? If current is directly proportional to voltage, it means when something is directly proportional, it doesn't just mean that when one increases, the other increases. Exactly, you must mention that both of them must increase at the same rate. So if one thing is directly proportional to the other, it means as one increases, the other also increases at the same rate. So if one doubles, the other also doubles. So which one is the independent variable here, by the way? Which one determines the other? Are you sure? It is the potential difference that determines how much current that flows. It is the difference in height here that determines how much water that flows. So in this case, the difference in height is like the independent variable, is it not? The amount of water that flows is the dependent variable. In other words, the amount of water that flows depends on the difference in height. The bigger the difference in height, the more the amount of water that flows at the same rate, or increasing at the same rate as that increases. So if we say current is directly proportional to voltage or potential difference, which one is the independent variable? The potential difference. The voltage is the independent variable. It is what determines the amount of current. If potential difference increases, current also increases at the same rate. We talk about all these graphs later. We're going to talk about these graphs later, but I just want to show you this. I need to talk about resistance, first of all. We've talked about current. I've talked about voltage, which you can think of. By the way, voltage is the technical name for potential difference or electromotive force. I will explain all that in details. We measure voltage using an instrument called a voltmeter. And the voltmeter is always connected in parallel. Right? Yeah. Voltage is measured in volts using an instrument called a voltmeter connected in parallel. Now, resistance R is the amount of opposition to the flow of current. So if you have a higher resistance, it means lower current will flow, isn't it? So if you want higher current, what should you do to the resistance? If you need higher current to flow, what should you do to the resistance? No, I'm talking about resistance. If you need a higher current to flow, what should you do to the resistance? Remember, resistance is the amount of opposition. See, if there is so much opposition, it will reduce the current now, isn't it? If you need high current, you need to reduce the opposition. If you need smaller current, you need to increase the opposition. You can think of the opposition as a valve placed here. If we have a valve placed here, I don't know how we can think of a valve as something like this. You have a valve placed here, such that the valve stops or controls the amount of water that flows. When you tighten the valve, fewer water will flow. So tightening is more resistance, smaller current. When you want more water to flow, what should you do to the valve? Loosen it. So reduce the resistance, more water will flow. I said all of that to say this. Resistance is the amount of opposition to the flow of current. And of course, resistance is measured in ohms. This is a symbol for ohms. Let me bring it out a bit. Yeah, resistance is the amount of opposition to the flow of current. Resistance is measured in ohms using an ohmmeter. If you increase resistance, current decreases. If you decrease resistance, current increases. All right. There's another way we can look at electromotive force and potential difference. Don't forget that both of them are actually what we refer to as what? Voltage.
Yes.
Okay. Just a moment, let me show you.
So they're the same thing.
They mean related concept, slightly different. Both potential difference and electromotive force can be referred to as voltage. In fact, voltage is basically the technical name for potential difference and electromotive force. Now, you think of potential difference as the voltage across 2 points in a circuit. You will understand it with this diagram. Let me show you this diagram. Look at this. Of course, we identify the circuit. What does this represent? The what? The battery or cell.
Yeah.
When you have many of them, you have battery. What does this represent? Switch. What does this represent? This is light emitting a diode, LED. It is emitting light, it's giving out light. What does this represent? Light dependent resistor, LGR. We'll talk more about all the other components. What does this represent? That's a variable resistor, meaning that the resistance can be varied, changed. I will explain more. This is an electric bell, that's F. This is a buzzer. This is a fuse. This is a standard or fixed resistor. That's a lamp or bulb. Okay, so let me just expose them so that we see properly. Some of them I have to write their names here, but you can see each of them. I wanted to explain to you the difference between potential difference and electromotive force. Both of them are about voltage, isn't it? Potential difference is the voltage across any 2 points in a circuit, like from here to here. Let me call this point P and point Q. When I'm talking about the voltage across P and Q, it is a potential difference. Now, electromotive force is actually the maximum voltage. Especially, you can only get that when the battery or cell is not supplying a current. And that is not possible. There's no way you can even measure the voltage when it's not supplying current. So there's a way we do it. We have to extrapolate to get that. I will be saying things that you will understand later as I'm continuing, right? But for now, think of electromotive force as the maximum voltage of the power source, while the PD are the voltages across any 2 points, any 2 points, any 2 points, any 2 points. For instance, there could be a potential difference across this light emitting diode, a potential difference across this light dependent resistor, a potential difference across the lamp, across the fixed resistor, across the fuse, across the buzzer, across the electric bell, across the variable resistor, across the switch. Different potential differences. That is potential difference. Any 2 points, like between P and Q, that's potential difference. The voltage across any 2 points. But electromotive force is what you get when you add up all of them. All the potential differences in any given loop. In fact, there's a law we call Kirchhoff's law. I will read it later. Kirchhoff's second law. it says that in any given loop, in any what? Like when you move around a cycle, like from one positive side of the battery back to the negative side, all the potential differences will add up to give you electromotive force. So the sum of all the potential differences is equal to the electromotive force.
So this circuit potential difference would be the distance between each of the components.
Yeah, you think of potential difference as the voltage we get between here and here. Remember, the voltage is how much push is given to charge between here and here. You can think of voltage as how much push we give to charge between P and Q. The amount of push we give to a charge between P and Q can be different from the amount of push we give to a charge between another point. It depends on the component you have there. Assuming this place is now S and this one is T. If you have maybe just your phone here and you have a heater in another point, they will definitely have different pushes. The one that has a heater will require more current, so it will have a bigger voltage. So the amount of push we have across 2 points in a circuit is the potential difference. It doesn't have to be the same all around. It depends on the components you have there. If we have a smaller component here, it will have a smaller voltage because we just need smaller current there. Also, we just need a smaller push on the current there. We just need a smaller push on the current there. If you need a bigger component like a heater, you will need a bigger push to force the current through. So it will need a different voltage. So between one component to another, from one point in a circuit and another point in a circuit, across it shows you the push there, which is the potential difference. Now in this entire circuit, if you add up all the potential differences, they give you the maximum voltage of the power source. I don't want to jump the gun because we go straight to Kirchhoff's laws to explain all that. But I'm just trying to tell you for now that the sum of the potential differences will equal the electromotive force because it is the power source that produces the push. It has a particular push here. Just for illustration, if I had 50 units of push, and what's that unit, by the way? V. If I have 50 units of push from the, sorry, where did I even put the 50? I have 50 units of push from the battery, which is 50 volts. 10 volts can be around here. Maybe 8 here, 10 here, 15 here, 2 here, 3 here, and so on, until all of them will add up to become the 50 distributed all around. So in any given loop, when you add up the potential differences, you will get the electromotive force. So think of the electromotive force as the maximum voltage across the power source. Maximum voltage across the power source. So that's why I'm going to define it that way. For now, I will give you a broader definition. Because I want to take this thing step by step, line upon line, precept upon precept. I don't want to jump the gun. You will be getting broader understanding of each of these steps. So I said PD is the voltage across components or any 2 points in a circuit. Did you see that? PD. That stands for what? Potential difference is what? The voltage across components or any 2 points in a circuit. While EMF is what? Maximum voltage across the cell or battery, assuming no internal resistance. Now that's another concept you will do at A levels. Assuming no internal resistance, the maximum voltage from the power source is the EMF. And for it to have the maximum voltage, current shouldn't be flowing, but that's a different discussion. So EMF is the maximum voltage from the power source. PDs are the voltages across components or any 2 points in a circuit. So in any given loop, you know, I've been saying loop, you'll be wondering, why do I have to specify any given loop? Because there can be several loops. Like incidentally, this one has only one loop, what we call series circuit. I won't jump the gun, we'll get there. In any given loop, when you add up all the PDs across these components, it will give you equal to the EMF. There could be several loops, like this one. Look at this circuit. It has several loops. Several loops means you can start from the positive side, follow a particular route, and come back. That's one loop. I can follow another route and come back. That's another loop. Another route and come back. That's another loop. In any given cycle, all the PDs you will pass through will sum up to with that. You will get to understand all of that. I think we have to just move straight to the discussion on each of these. Before we talk about, we look at Ohm's law separately. So please, let's go to types of circuit connections. Are we ready for that? Let's go. First of all, a circuit itself is a symbol diagram that shows how the current flows through the components. Using symbols to show how the current flows through the They could be parallel, they could be series. It could be parallel, it could be series. A circuit generally is a symbol diagram that shows how the current flows through the current components. We use symbols for the components and represent how the current goes around the components from one part of the cell, go around, or from the current starts from one part of the cell, goes round, and comes to the other side of the cell or battery. So what you've seen here is a circuit. So, is that noted? All right. You're right. Let me just describe it. First of all, you've written about what circuits are. There are two types of circuit connections: series circuits, and the other one we call parallel circuits. In a series circuit, the components are connected end to end. This is not showing properly, so let me leave it the way it was. In a series circuit, the components are connected end to end, such that current flows through just one route. It has only one route to flow. In other words, when current starts from here, it cannot branch into any other route. It flows through this only one route to pass through all these components. Compare it with this other one, this parallel, where the current can flow through this particular route, or another one, or even another one. So in a parallel circuit, the current has a choice of routes. But in a series circuit, current can only flow through one route, only one route. So components that are connected in series have the same current flowing through them, because the current didn't branch out. What I mean by branching out is, do you know that current can flow up to this junction Q, and then some will flow through this route, another will flow through the other route, and get to here and branch out again. That is in parallel. Current branches out to several routes. So different current will be flowing through different components in parallel. But for series, since the current didn't branch out, it is the same current that flows through all components in series to each other. In fact, we say that current is the same everywhere in series. All components connected in series have the same amount of current flowing through them. Did you hear that? Since all of these things are connected in series, they have the same amount of current flowing through them. Because in series, components are connected end to end, so that current flows through just one of them. So if you compare it to parallel, current has a choice of routes. So in a parallel circuit, current has a choice of routes. So it can flow through two or more routes. Did you get that?
Yeah.
While current is the same everywhere in series, it may not be the same in parallel, because a different current or a current that gets to Q can split. Some will flow through here, so it's a different current. Another one will flow through here, it's an entirely different current. But do you know that this component and this component are in series? Why? It's the same current that is flowing through the two of them.
Oh, you're right.
Once you have the same current flowing through components, they are in series. But if, let me actually explain what parallel means. For components to be in parallel, are you listening to me? This is very important. For components to be in parallel, when current gets to a junction and splits, they must reconnect again the same amount for those components to be in parallel. What I'm saying is, if current flows into here, let me see if I have a diagram that can represent this better. I drew a diagram somewhere. Yes, it's here. This is what I mean. I think I can zoom this in out a bit. Look at this. Current starts from the positive side of the battery, flows until it gets to here. I will call this junction P. Now the current splits at this junction. Some will follow this path through A and through C, back to E, to G, and back to the power source. That's one route. Some can flow through here. In fact, this one has several routes.
I thought connections have to be perpendicular.
Not at all. When you are connecting your wire, you don't have to make sure they are perpendicular. In drawing, yes, but in real life situation, not necessary.
No, I was talking about it.
No, it's even in this kind of drawing, at this level, you don't have to make them that way. You can have components split coming out from different nodes.
Yeah. Oh.
So how will you make all of them perpendicular if you have several of them coming out from these several nodes?
Yes.
You know, there could have been another one coming out from here again, flowing through another route. So they don't have to be. But when you have just two, yes, when you have just two, it is neater to make this one come out perpendicular this way and comes back, come out perpendicular this way and comes back. Yes, it's neater. I mean, I could have removed this thing and drawn it like this. It's just convenience. It's not like it must be. This one could have been like this. This one like this, so that it will look like they are coming, because it's just two, so we can afford to make them come out like perpendicular. You get that? You know, I was trying to tell you that for components to be in parallel, watch it though. A current that splits at a particular point, like splitting at here, I will call M. You know, it flowed into this junction P, split, some flowed into the switch 1, and still meet another junction. If they split at this junction, some will pass through A, some will pass through B, but they must meet up again for those two components to be in parallel. So if current that split at a particular point meet up again at another point, I will call N. It means the components they flow through are in parallel to each other.
If five of them, if there were like, let's say 5 rods from one point.
Yes.
Does that mean those 5?
All those 5 components
have to meet
are in parallel, and current passing through them must meet up again. If they don't meet up again, they are not in parallel.
So what is it parallel?
Parallel means, the way you can understand it, for two components to be in parallel to each other. In fact, that is a very important question. For two components to be in parallel to each other, a current that splits at a junction, like I said, must go through those routes or those routes and meet up again. Let's see. A and B are in parallel because the current that split at M, a part flowed through A part flowed through B, and they met up again at N. You know, the entire current from here poured into N. So A and B are in parallel. But let me show you something. Watch this again. At P, current can split at P, flow through here to pour into here. What can we call here? Let me give a letter Q. Current can split at P, right? Flow through here, through A, through C, and pour into Q. Or it can flow through here, watch me, through D, and pour into here again. So A and C together, A and C together are in parallel with D. A is not in parallel with D alone. Why? Because the current that split at P is not the exact current that passed through A and through D that met. If you know, some parts also went through B. It's a little bit confusing, so I have to explain it further. All right, look at this. Oh, you need to see it. Just a moment. Because you need to see the current flows to provide components in parallel and so on. I hope you can see this diagram. Let's start again. Current from the positive side of the battery flows until it gets to P. It splits. Some went through this route, some went through this route. All of the current that came into here, all of the current that came into here must pour into here. And whichever route they pass through, those things are in parallel. Now let's see. This is more complicated. Let's use this smaller route. I will incorporate the other route. From M, these are the two different routes it can flow. A through C until it gets to Q. B through C until it gets to Q. And we have established that A and B are in parallel. Why? The current, yes.
They flow through different paths, but when they meet,
they combined again. And it was the same amount of current that entered that will be leaving a junction. In fact, between two junctions, this is another way you can understand it. Between two junctions, if the same amount of current that came in is what is leaving, the different routes they pass through are in parallel. In any two junctions, M and N, if the amount of current coming in is the same amount of current leaving at the other junction, the different routes the current pass through are in parallel. We can say that E and F are in parallel. Why? When current from here, Q, split. So, oh, you've seen F. This is F. This is E. Current from Q poured into two routes. Some went through here, some through here, and they combined again at this junction, which I can call any letter Y. But check these things. Check A and check components A and D. A, this lamp A and lamp D. Let's see if they're in parallel. I'm talking about lamp A and lamp D. Let's see if they're in parallel. Are you ready? At P, the current splits. Or the current pouring into here The next junction, they must all combine. And all the routes they pass through are in parallel. Let's see. It poured into here, went through A, and see where it is meeting. Went through C, D. See where it is meeting Q. The one that passed through A did not flow directly to Q. It collected something else before it went to. Let me use values. It makes sense when I use values. Don't worry, you will get it better here. What you do? I'll use value to just make it illustrate better. Because that's actually what happens. In fact, jumping the gun, I should have told you this before even coming into all of this. This is better for you. You will understand it better like this. Don't worry, I'll come back to that diagram. So let's look at features of the two circuit connections. Features of series and parallel. Now, current is the same everywhere in series. All the components that are connected in series, the same current flows through them. You know, this entire circuit is parallel because some current can flow through one route, some through another route, through another route. But even in this parallel, there are some components that are in series. Like this lamp here and this lamp. Why are they in series?
Because they have
the same amount of current flows through them. Because once you have the components connected in such a way as that the same amount of current will flow through them, they are in series. The components are connected end to end so that the current flows through just one route, the same amount of current. I could have just said the same amount of current. The components are connected end to end such that the same amount of current flows through just one route, flow through them, only through one route. But once it can find its way through different routes, they are parallel. So current is the same everywhere components are in series. Noted? Voltage is the same everywhere components are in parallel. In other words, the components that are in parallel have the same voltage through them. I told you that A is in parallel with B. The voltage across A must be the value of the voltage across B. Voltage is the same everywhere in parallel. Components that are in parallel have the same voltage across them. Components in series have the same current through them. I'm using certain terminologies. We say current through, voltage across. That also determines how the
Is there a difference?
Yes, because the instrument we use for measuring them, if you remember, I told you that the ammeter is connected in series. You know, I told you the ammeter that we use for measuring current is connected in series. That is connected end to end to the component you want to measure its current. While the voltage or voltmeter is connected in parallel. Simple illustration will explain this. I should have a connection somewhere to show this. Okay, this is fine. Interesting. I just zoom it in to reveal it better. Look at this circuit. Can you see this circuit? See this fixed resistor. If I want to measure its voltage, it has to be connected in parallel. In what? So that when current gets into a junction, it splits, passes through the voltmeter, and also another one through the component, and then they will meet up again. Voltmeters are connected in parallel across the component you want to measure their voltages. But look at the ammeter. I want to connect an ammeter that will measure
this resistor. How did I connect it? In series. How did I connect this ammeter? In series. I didn't have to produce another wire to connect it in parallel. Ammeters are connected in series.
Okay.
Voltmeters are connected in parallel. If you notice, anywhere I have a voltmeter, it has to be, you get another line to put it there. Another line to connect it. Another line to connect it. So voltmeters are connected in parallel. But when you're connecting an ammeter, just on that same route that you want to measure its current. So because current through, so it should be along that same route where the current is flowing to be able to measure the current there. Because current is the same everywhere in series. If you want to measure the current here, whatever you're going to connect must be in series so that it can actually measure the same current through that component.
Yeah.
And voltage is the same everywhere in parallel. So if I want to measure the voltage here, I have to connect something in parallel to it. This is too much information, right?
No, my level is also.
Okay. If I want to connect the voltage to measure this if I need to connect the voltmeter to measure this voltage, I have to connect it in parallel because I said voltage is the same everywhere in parallel.